Okay, this is a question about the changing volume of a bubble that's rising in water. Okay, now why would the bubble expand? And it does expand. And let's think about this. Okay, the bubble starts at the bottom, or starts at a great depth of 50 meters, and it rises up. And as it goes from here to here, what's happening is it's rising up in the fluid column, and it does that, it's going to lower and lower pressures. So as it goes to lower and lower pressures, it's going to go to bigger and bigger volumes. So the bubble will expand as it rises. And we need to compute the final volume. And if we know the final volume, we can calculate the final diameter. Now, another thing that happens is the temperature changes. So first, we're going to do two parts of this problem. First, we're going to look at the change in pressure in the fluid column. Second, we're going to look at the change in volume of the bubble as its pressure changes, but also as its temperature changes. And that's an echo of some of the stuff that we saw in chapter 12. Now let's do our preparation, okay? And we'll prepare by doing this. We're going to say, look, here's the bubble at the surface, and here's the bubble deeper down right here. Clearly, there's a higher pressure here than there is here. And we have a relationship that was given in chapter 13 of the pressure at depth. The pressure at depth is equal to the pressure at the surface plus rho times g times d. Okay, now P0, that's the pressure at the surface. And at the end of the problem, the pressure is just at the surface here. This is just atmospheric pressure. That's 101,300 pascals, okay? And that number appears in this relationship right here. Then we have this pressure plus rho times g times d. Rho is the density of the fluid. Well, it's fresh water. Fresh water has a density of 1,000 kilograms per cubic meter. D is the depth in the fluid column, and we know what that is. This is 50 meters because the bubble starts out 50 meters below the surface. So we have everything we need to calculate the pressure at depth. Now we're going to think about this as a gas law problem, okay? And as the bubble goes from being down here to being up here, its pressure changes. It goes from PI to PF. Okay, and this right here, this is PI. That's my initial pressure. This pressure is my final pressure. Okay, that's my PI and my PF. Its temperature also changes. It starts at an initial temperature and it ends at some final temperature. Now we know the temperature it starts at, and we know the temperature that it finishes at because we assume that the bubble is in thermal equilibrium with the surrounding water. So it starts at 10 degrees Celsius. But when we do gas law problems, we don't use Celsius, we use Kelvin. So I'm going to put this in Kelvin. 283 Kelvin is where it starts, and then it finishes at 293 Kelvin. And you can see the difference in the Kelvin temperature isn't that great, and so that's not going to be a big determinant of the final volume. Finally, it starts at a certain initial volume, ends up at a certain final volume. And we know the initial volume. It's a sphere, it's a spherical bubble, so its volume is 4/3 pi times initial radius cubed. And let's just leave it like that for now. And then the final volume is just 4/3 times pi times the final radius cubed. And let's just leave it in that form for now. And with all this information in hand, we're ready to proceed to our solution. Now, the first thing that we're going to want to calculate is what is PI and PF. Okay, PF, we know what that is. That's 101,300 pascals. How about PI? The initial pressure at the bottom is equal to P at the surface, which is this number right here, plus rho times g times d. So it's 101,300 pascals plus rho, which is the density of the fluid, which is 1,000 kilograms per cubic meter, times g, which is 9.8 meters per second squared, and then times the depth, which is 50 meters. If we compute this, we get a final answer for the pressure at depth of 591,300 pascals. Now notice, this number right here is approximately 6 times the pressure at the surface. So if temperature isn't a big factor, and I don't expect the temperature to be a big factor because it doesn't really change by very much, if the pressure goes down by a factor of 6, I would expect the volume to go up by a factor of 6. And we can use that as to help ourselves out with some assessments. Now that we have the pressures, we have the temperatures, and we have the volumes, let's go ahead and relate the initial and the final pressure, volume, and temperature. And our most general relationship for that is this: Pi times Vi over Ti is equal to Pf times Vf over Tf. And this relationship is true for a sealed system, but it's a bubble, and we can assume the bubble is basically a sealed system. It doesn't exchange gas with the water. So we can use this relationship to solve. And what we want to look for is Vf. And we're going to solve for Vf and relate it to Vi. So I'm going to take this relationship and rewrite it like this. Vf is equal to Vi times Tf over Ti times Pi over Pf. That's my basic relationship. Now, I'm going to go ahead and rewrite Vf as 4/3 pi times Rf cubed. I'm going to write Vi as 4/3 pi Ri cubed. And I'm going to note, we know what these numbers are. Okay, we know Tf, we know Ti, we know Pi, we know Pf. We have calculated all of those numbers. Here are our temperature numbers, and here are our pressure numbers. So we can take these numbers and we can put them in here. But before I do that, I can do some canceling, because notice this: the 4/3 appears on both sides of the equation. Pi appears on both sides of the equation. And so I can just compute Rf cubed is equal to Ri cubed times these two fractions. And if I put in the final temperature and the initial temperature and the initial pressure and the final pressure, I get this number is 6.043. Oh, and that's good, because we said the volume should get bigger by about a factor of 6. But we're not computing the difference in the volume, we're computing the difference in the diameter. So what I'm going to do is take a cube root of both sides of the equation, and I'll say this: Rf is just equal to Ri times the cube root of 6.043. Notice I've kept an extra significant figure because this is an intermediate stage of the calculation. Now I'll multiply both sides of this equation by 2. So 2 times Rf is equal to 2 times Ri times the square root of times the cube root of 6.043. Okay? Well, this number I can calculate. The cube root of 6.043 is 1.82. And notice this: 2 times the initial radius. Well, 2 times the radius is just the diameter. So this is the initial diameter. 2 times Rf, again, that's just the final diameter. So the final diameter is equal to the initial diameter times 1.82. The initial diameter was 1.0 centimeters. So I take 1.0 centimeters, multiply it by 1.82, and I get a final diameter of 1.82 centimeters. Okay? And I'm going to round that, because it's a two significant figure problem, to 1.8 centimeters. And it's reasonable to give the answer in centimeters because that's what it was phrased as. And let's just assess this. Okay, the volume or the diameter has increased by a little less than a factor of 2. When I cube this, I get something like 6, and we said we expected the volume to increase by about a factor of 6. So our final assessment is that this problem matches our understanding of how the world works.